Hello, hello, hello. Let's continue thinking about free stuff, but this time let's take it up a notch. So before we were thinking about free monoids, but now I would like to think about free categories. So we know that there is a category of categories, right? So in the same way that we created free monoids on sets, we could imagine to create free categories on something. So the first thing we have to think about is on what, right? So maybe you first think, let's do it on set. And there certainly is. So we know that free stuff means left adjoins to the forgetful thing. There certainly is a forgetful functor this way, right? Where we are just taking the objects of the category and we are forgetting about the morphisms. So just call this obj. But then the funct, and this has a left adjoint, so that's good news. But this is just creating the discrete category on a set, right? So the one where you have a bunch of objects, but the only morphisms are the identity morphisms. So that's not very interesting in a way. It doesn't give us much structure as we want. So what we could do instead is we could consider a different category to start from here, which is the category of relations. So here the objects are relations, and again there is a way to forget some structure from categories where we are taking the hom basically, right? So if we think of a category like this, we have a bunch of objects. Okay, what really makes it a category is, well, so we have some arrows between these things, right? So what really makes this a category, of course, is that we have identities at each object. And if I have one morphism here and then one here, then I must have their composite, right? So we have identities and composition. But if you forget about this structure, what we get is just a bunch of objects and arrows between them, right? That's exactly a relation. So that's another way that we can forget about the category structure. We forget about, not about all the morphisms, but we forget about that there is identity and composition, right? And then we could ask, is there a way to go the other way here, such that this again is a left adjoint? And now we have to get careful about the arrows. I think it should be pointing this way, right? Still. And it turns out that there is. And again, it has a kind of intuitive description, right? Where we want to add in, so we start with some relation like this. So we have a bunch of objects that we want to keep, and we have some of them are related to other ones. But it could be that first of all we don't have, so we could have some identities, but we don't know that. We could be missing some identities, right? So we need to add these in, and it could be that we have this one and this one, but we don't have their composites. We need to add that in as well, right? And then in order to do this in an associative way, you have to do it similar to what we did for the monoid and say that the morphisms in our free category are going to be lists of morphisms in the original category, right? And then we can again concatenate lists to compose the morphisms. So this is going to be, this is our f, and then f of r is going to be r star, which is the reflexive transitive closure of R. And this star here is meant to be Kleene star from automata theory, right? So it means you can iterate this as many times as you want, 0 or more. 0 for reflexive, more for transitive. Okay, so let's see if we can do this. So first of all, we need to define this category of relations, right? So I'm saying here it is. The objects are a choice of a set A and a relation on it. So we have some set and some relation. For example, this could be the natural numbers and this could be less than, or this could be booleans and this could be maximum. I don't know. Is greater than, I guess. So that's the same example. Sorry. And what is a morphism between these things? Well, so I have one relation on A and I have one relation on A prime. And a morphism, I'm saying, is a function on the underlying sets which preserves the relation. So if A and B are related in the original R, then f of A and f of B must be related in R prime, right? So it's the structure preserving maps again, right, where the structure is the relation. And then the identity is given by the identity function, which certainly is relation preserving, right? And composition is given by underlying composition, which again is relation preserving because both parts are. So, and then it's easy to show that this is associative and preserves and has identities. Okay, so we can now go from categories to this category relations, where forgetting that we have identities and composition, right? So how does this work? Here I have to give a set, an underlying set, and then a relation on it. So my set is going to be the objects of my category, and my relation is going to be my home. So I'm saying that two things are related if there is a morphism between them, which most probably is not a propositional relation, right? There's probably many parallel morphisms, so that's fine. We're not asking for this to be propositional. Okay, what about the action on functors? So f is a functor from A to B. Then here I have to give an underlying map on the underlying sets. So I define these to be the objects. So this is exactly the action on objects of f, right? And now here I have to show that I preserve the relation, but I define the relation to be the home. So this is exactly the type of the action on morphisms of f. AB goes to f map f. Okay, and then it's easy to show that this preserves identities and composition again, right? Okay, so here is the star of the lecture, where we take a relation R on A and we upgrade it to a new relation on A, which is now reflexive and transitive. So reflexive means that we're adding in all of these identities from A to A, right? And transitive means that if I first can go from A to B using R, and then I can do possibly many more steps, or just 0 more, or many more if I iterate this constructor, then from B to C, then I can go from A to C. So this is doing transitivity by having a list of these, basically, right? And then you can prove that you can do many steps. So if I have a whole bunch of steps from A to B and a whole bunch of steps from B to C, and I can concatenate them to get steps from A to C, this operation is associative, and preserves identities, and all the things you expect from lists. Just that these are now typed lists, right? Where we really keep track of where we start and where we end. And then we can use this to define the free category where the objects, so free category on a relation, the objects is the same as the underlying sets of the relation, but instead of just using R here, which wouldn't work, we take the reflexive transitive closure of R, right? With reflexivity as the identity and concatenation as composition. We're really putting these paths together, one after the other, right? And all the proofs are the same as the proofs for lists that we used for monoids. So it really is very similar to monoids in disguise, right? And then let's show that this is actually an adjunction. So this really is the free category. So what do we have to do? Well, we have to define these to and from maps. So here we are given a, let's see, we are given a functor from the free category to B, and we have to produce a morphism of relations. So that's given by two things, right? Something on the underlying thing. So this should go from the first projection of X to the objects of B. So what happens if we look at the action on objects of F? That's exactly what we want here. Okay. And here we should take an A and a B in relation. We should preserve it. And so now we know it's something in the hom between F of A and F of B. That sounds like a job for F map of F. You give it something. Okay, and what should we give it? Well, we have an R from A to B, and we want an R star from A to B. So we can make a singleton out of this, right? Just like we did before. So we're saying one step is the same as one step followed by 0 steps. Okay, and then we use the same kind of thing. So this fold star, of course, I defined from what I needed here, but now I've done it already, so I can just fill it in. And these proofs are very similar to what happened in the monoid case as well, right? So we can fill all of that in. So we see that this construction really is the free category. It's the smallest category on a given relation. And you might recognize this from what we used in the solver, right? Where we used exactly the reflective transitive closure of these map piles to interpret, as it turns out, also paths of morphisms, right? So this is not a coincidence. The free category is often the syntax for things. So here is the syntax for categories. So it's the thing where free thing is the syntax, because the syntax only mentions the bare necessities, which is exactly what the free things does, right? So this finally explains why we proved the things we did here to make this work. So here, for example, that we preserve composition. Maybe that wasn't so hard to figure out, but this Kleisli star lemma is a little bit more mysterious, right? So here, return really is the singleton. So we see that this Kleisli star lemma here, which wouldn't be so easy to come up with on your own, why this is what you need at this point, that corresponds exactly to this lemma here, right? Here's the singleton, here's the F map, here's the fold star, which is the Kleisli star from here. So now we know where it came from. It came from the fact that we had a free adjunction, a free forgetful adjunction. So that's why we knew that that was the right thing to prove at that point.